This is session 4 for models in epidemiology and biostatistics. My name is Gordon Hilton Fick. In session 3, we saw logistic regression for the first time. And what we did was we looked at 3 models for a circumstance in which we had a disease exposure relationship of interest and 1 potential confounder modifier. And we went through all of the issues crucial there that impact on using models instead of using stratified analysis. And what we saw was some things that were the same or nearly the same, and some things that were slightly different. So for session 4, we're going to be looking at the circumstance we saw in session 2. We're going to be considering a disease exposure relationship where there are now 2 potential confounder modifiers. And for illustration, we'll use age, young, old again, and gender, male, female again. And we'll speak of a disease exposure relationship. And we'll couch it in terms of a case control study, but again, this will be minor matter insofar as the key ingredients that we'll be exploring are concerned. Just a reminder that we then have 4 strata. Again, we have the young women, the old women, the young men, and the old men. We'll label these strata 1, 2, 3, 4, and I'll be coming back to that labeling of the strata in a latter part to this session, because there will be some ability to compare things we see in session 2 with things we're going to do now in session 4. So, what have we got now? Well, although not maybe explicitly stated back in session 2, we've now got 8 probabilities for consideration, or 8 odds. And they correspond to these 8 groups. For example, we have the young women who are cases, who have disease. And then we have the young women who are controls, who do not have the disease, and so on. So we then see that there will be 4 odds ratios. 4 odds ratios that can be interpreted then as the odds of exposure for cases and the odds divided by the odds of exposure for controls. And we can see that there's 4 of these odds ratios here. For example, there will be an odds ratio for the young women. And the interest is in the disease exposure relationship, and it's going to be captured by the use of the odds ratio. But how do we get there? How do we get to, in some sense, a correct assessment of the disease exposure relationship then? Well, what did we do back in session 2? Well, we looked at the 9 2x2 tables that we could see as grouped into 2 kinds. Joint stratification on age and gender, or simultaneous stratification on age and gender. Stratification on age alone and ignoring gender. Stratification on gender alone, ignoring age. The first analysis is sometimes called a joint analysis. And sometimes the second and third analyses are called one-at-a-time analyses. There's other names that are often seen too, but we'll use these. So what did we do? With the 4 strata, we had a test for the homogeneity of odds ratios. That was the Mantel-Hansel test. It had 3 degrees of freedom, testing the null hypothesis that all 4 of the odds ratios are equal. And then we referred to the notion that such a test was omnibus, and that it doesn't tell us how the odds ratios are different, but rather that they have the potential to be different. The null hypothesis here, rather unspecific, if I may, just that all 4 odds ratios are the same. Omnibus, of or dealing with or providing for many different things or cases, providing for many things at once. Yeah, that's an omnibus test. Then, if we were to, on the basis of some methodology, including the test of significance, if we were to make the assumption that there's no difference among the 4 odds ratios, then we come to the assessment of the assumed common odds ratio. And we have, from our stratified analysis, the Mantel-Hansel estimate of the assumed common odds ratio, sometimes called the adjusted estimate, which would then be compared with the crude. If we are prepared to assume that the 4 odds ratios are the same, then we are in the position to be able to address confounding. And the null hypothesis that is under consideration is that the assumed common odds ratio is 1 that we have available to us. And we have also the 1 at a time assessments. We have the 2-by-2 tables. Would this analysis alone have identified age as a modifier? Would this analysis alone have identified age as a confounder? And maybe more crucially, would such a simpler analysis have identified the issues correctly from that would be in agreement with that we have already articulated in the joint analysis? Because if the joint analysis leads us to a certain set of interpretations that are different from this 1 at a time assessment of age as a potential confounder modifier, then the joint analysis will be viewed as the correct one, for obvious reasons. And the same matter is of interest with gender assessment. Those are the issues that we have. Again, the joint analysis is almost certainly going to be preferred if the 1 at a time analyses miss the issue. And we've seen this from the fairly theoretical material that we saw in session 2, and then again with the illustration that we saw in session 2. Okay, so this is essentially a restatement of what I just observed. Do we need the joint analyses, or will the 1 at a time analyses be sufficient? You can't know whether the 1 at a time analyses are giving us the correct directions until we assess the joint analysis. In other words, if we are, say, for some reason, deciding only to use the 2 1 at a time analyses, we have to appreciate that there are assumptions implicit in doing only the 1 at a time analyses. Do we get led astray? And that, if you've had some time working through the illustrations, the 8 different data sets that I gave you in session 2, there's Lots of different possibilities. So now we'd like to say, okay, we've done this as far as we could with the stratified analyses. Yeah. Now we'd like to think, okay, let's talk about the models. Let's see, how do we go about using this model, this logistic regression? But the first thing we need to notice is that, there's a lot of models. There's 8 unknowns, the 8 probabilities, or the 8 odds. Well, so that means that there's in principle a huge number of models that might be considered. How do we exclude many of them from our attention? How do we ensure that we've addressed all the key issues? Now, there are certainly some who would argue that, well, in this age of fast computing, addressing or at least in principle determining all of those 256 models isn't out of the question. But the challenge then is, what do I do with all of them? How do I apply principles that are at least in simpatico with the finest of epidemiologic assessments? Well, this is a complicated question, and we'll see that even with what appears to be still a comparatively simple project, that is, a disease exposure relationship with 2 potential confounder modifiers, that, well, what can we do? It could be that the soundest approach, and again, there's many caveats here, but if we can, it may be that starting with a model that has all 8 of those coefficients is the place to start. So P is the probability of exposure here, and then we have 8 terms. Now this may again look like, oh no, this is going to be impenetrable. How am I going to possibly understand this model that has all 8 of these terms? Notice all of these products here. And now we've even got a term with 4 terms. Beta 7 times A times G times D. Oh my. That looks, you might be thinking, and sometimes people do take a look at that and think, I'll never understand this. Well, I'm here to tell you that you can. And in fact, I'm going to give you an approach that leads to the correct interpretations, and it isn't as hard as one might think. Is it time-consuming? Perhaps, can be. There's many issues? Yep. But are they out of the question? Are they impenetrable? No way. They're available to you. So let's take that model and notice that, and I'm skipping all of the hard work, but this model gives us 8 log odds expressed in terms of the regression coefficients. In fact, we can see straight away, if we go through this process, that we have an interpretation for one of the regression coefficients straight away. It's alone here, yes. And what is that? Well, that is the log of the odds of exposure for the young women who do not have disease or other controls. Let me just repeat that. Beta naught, we can now see from that complicated model, is nothing more than the log of the odds of exposure for the young women who are controls. That's not so bad. Now we can see that there are 1, 2, 3 terms here that involve only beta naught plus something else. Let's take a look at those, just to give us a bit of a foothold on things. What is beta naught plus beta 2 here? Okay, well that's the log of the odds of exposure for the old women. who are controls. And what is beta naught plus beta 3 here? That is the log of the odds of exposure for the young men who are controls. I think I've got that right. Young men who are controls. There it is. So we then can see that we have comparatively simple interpretations for beta 2 and beta 3 by taking differences. Not too bad. Well, let's see if we cannot then present this in a manner that might help us as we move forward here. Let's look at the model that gives us 4 log odds ratios. So we might have been tempted to think, okay, let's look at some of those coefficients we can interpret. But maybe the more crucial ones are the ones that involve the log odds ratios directly. Let's look. Beta 1, we can then see, is the log odds ratio for the young women. We might have been able to see that fairly directly from before. Now what do we get? Okay. We've got that number figured out. What does that say about beta 5? Beta 5 is a difference between these two things. Okay. That's the difference between two log odds ratios. And it is a difference between the old and the young for the women. So beta 5 is capturing a measure of the difference between two log odds ratios for the women. The difference between the old and the young. So this is capturing the impact on the odds ratio, the difference between the young and old for the women. And that's beta 5. Let's continue with this and see that beta 5 plus beta 7 is the difference between the log odds ratio for the old and the young, but for the men. Aha! Now we're getting on to something. This difference then, the difference between beta 5 plus beta 7 and beta 5, is that last thing, the beta 7. That's a difference between two differences. So it's the difference between the old and the young for the men and the old and the young for the women. In other words, this is going to tell us about whether or not the difference between old and young for the men differs from the difference between old and young for the women. In other words, we've got an interpretation for beta 7. Wow. Further, we can do the same thing by comparing the comparison between the men and the women who are young and the men and the women who are old, and we get exactly the same thing. Wowee. Let's continue. So what if this quantity beta 7 that I've isolated off is not 0? That says that both age and gender modify, and that the age modification is different for the men and the women. In other words, the age modification depends on gender. That was what we saw here, this difference between beta 5 and beta 7, plus beta 7 and beta 5. And it's interesting to notice that it's the same thing as asking, does gender modification depend on age? So with one test of significance, if we wish to test the null hypothesis that beta 7 is 0, we're getting two things at once. It appears as though we're getting two things at once. In fact, they're symmetrical statements. If gender modification depends on age, then age modification depends on gender. Okay. So these are symmetrical statements. The first statement applies the second statement and vice versa. Notice that is of interest to us. That is something that we didn't directly get to assess from the stratified analyses. We might have seen it qualitatively from the odds ratio estimates we got from the illustration we looked at. But we didn't have a means of testing that. So this logistic regression approach is giving us the means to assess whether or not age modification depends on gender, which is the same thing as asking, is gender modification dependent on age? Okay. And that could be argued is part of the rationale for starting with that complicated logistic regression equation with 8 terms. Because if beta 7 is not 0, we are probably then in a complicated situation in which the assessment of age modification needs to be done separately for the men and the women, and similarly, the gender modification needs to be done separately for the young and the old. We have indeed the most complicated of circumstances. So what about then if we are able to make that test of significance and we're prepared to say that there's no evidence against the assumption of beta 7 being 0? Well, we saw a hint of this with what we would do in class number 3, or in session number 3. All right. Let's then remove that term. If beta 7 is 0, then we don't have a term here that involves beta 7. We just have a model now with 6 regression coefficients. 7 regression coefficients. Now, if we repeat what we did earlier and construct the 8 log odds for this model now, and then the 8 log odds ratios, we get something interesting. So, again, there's a fair bit of, steps to construct this display, but if you do so, and then construct the corresponding odds ratios, we find something that's of interest. Now, let's look at beta 5. Beta 5 being the difference here between the young and the old for the women. And beta 5, we can see also is capturing the difference between the 2 log odds ratios, young and old, young versus old for the men. In other words, this is now assumed common. The difference between the young and the old assumed common to the men and the women. What about here? Now we've got the difference between the men and the women for the young, and the difference between the men and the women for the old. And again, we get the same characteristic. So this difference between 2 log odds ratios, this minus this is beta 6 plus beta 1 minus beta 1, and here we have beta 6 plus beta 5 plus beta 1 minus beta 1 plus beta 5. They're both beta 6. In other words, this is telling us about whether or not it's reasonable or possible now, it's possible to address the gender modification assumed common to the young and the old. And here we have the age modification assumed common to the men and the women. In other words, we've got now this assumed common issue popping up, but it's now much more specialized, isn't it? Beta 5 and beta 6 refer to essentially either age modification or gender modification assumed common to the other. In other words, we're getting at, with this model, the ability to address whether or not there is gender modification after adjustment for age, and whether or not there is age modification after adjustment for gender. So we can then see we've got a big issue in play here, and I hope you can see what's happening. We're going to have gender modification adjusted for age, which we then would like to consider gender modification not adjusted. And if, in fact, adjustment is meaningfully different from not adjusted, then we're going to have essentially what I will comment here is a form of confounding that's a bit more elaborate, but it's available. It's available for assessment. Both of them are. Okay. We've got that age modification is measured by beta 5. So if beta 5 is not 0, then age is a modifier, and this modification does not depend on gender. Further, if beta 6 is not 0, then gender is a modifier, and this modification doesn't depend on age. And as I mentioned, in both cases, we have here age modification adjusted for gender, and here we have gender modification adjusted for age. Yep. The modification description. Now, if this model, the model that we had that had the 7 terms in it, displays that both, let's just take, for example, that both age and gender modify, then we can consider the 2 one-at-a-time models, each with 4 terms, and identify the modification of the same form as in the big model. Okay. Now, if we still see the same form of age and or gender modification with the simpler model, then again, Occam's razor might be in play here. We might say, we didn't need all this elaborateness in order to see that age modification is present or gender modification is present. So, what you will sometimes see in the literature is that we sometimes see that age and gender somehow modify in some meaningful way if both beta 5 and beta 6 are non-zero. But what is interesting to notice is that age modification perhaps might only be seen by this so-called joint analysis involving all 7 terms. So you will see some authors who will say that age and gender jointly modify. I think that needs clarification. I think what we need to be able to see here is that, in fact, the age modification and the gender modification are only seen through a joint analysis. So some care needs to be used in this description. Now, again, it might be that all of this hard work with this model with 7 terms isn't really needed, and all we needed was the 2 one-at-a-time analyses in order to identify whether age and or gender modify. But if, in fact, the assessment of the age modification adjusted for gender differs from the assessment of age modification without adjustment for gender, then we can see that it was important to consider the model with all the terms in it. Okay, there's a whole range of other possibilities available here. And one of them, for example, might be where, say, beta 5 is non-zero, but beta 6 is 0. That age is a modifier and gender is not a modifier. Okay, in that instance, though, again, we're seeing age modification after adjustment for gender. So we may be in a position to say that gender confounds, but it's a little more elaborate, isn't it? It could be that gender is confounding the age modification. If, in fact, the analysis we do here differs from the one-at-a-time analyses. Absolutely, eh? Now, it could be argued that if we have beta 5 non-zero and beta 6 is 0, that we might want to consider a model that involves just the remaining 6 terms now. Should we be going to the one-at-a-time analyses straight away? Notice we're getting at another complexity to things. If, in fact, this were to be seen to be the case, we can then, again, construct the 8 log odds and then construct the 4 log odds ratios again. Notice that with this model, we're still seeing that beta 5 is capturing age modification assumed common to gender. But with this model, there is no gender modification after adjustment for age. So this is, again, a somewhat intermediate circumstance to the one-at-a-time analyses. And again, there may be matters that need to be given consideration here. This is one that I would say is comparatively unusual in practical contexts, but it's possible. Okay. What about if age is a modifier? What can we say about gender? Is the age modification confounded by gender? Well, I've already spoken to this. We would then consider the one-at-a-time model, and compare it with the model that had the 7 terms, or possibly the 6 terms. Okay? Same thing if we had the opposite case, where beta 6 is non-zero and beta 5 is 0. Again, we have this possibly important intermediate circumstance, and there's the differences again. And perhaps we get that gender is a modifier. And then what could we say about age? Is gender modification confounded by age? And again, this is typically addressed by considering the one-at-a-time model. Do keep in mind that there is that intermediate model too. Okay. What do we have then if, in fact, beta 5 is 0 and beta 6 is 0? Well, what have we got? We've got now a model. If we remove beta 5 and remove beta 6, we have a model that now has 5 terms. This is the model that enables the assessment of the disease exposure relationship adjusting for age and gender. Because if we're prepared to assume that beta 5 and beta 6 and beta 7 are all 0, then we have no age or gender modification. And now we're interested in whether or not we can report, or should be reporting, an assessment of a disease exposure relationship adjusting for both age and gender. So then we can ask whether or not age or gender confound or both. And again, we now have we're going to be busy because we're going to have this model here with 5 terms, and now we're going to have the consideration of these 3 models. In other words, where we have this particular model where we have adjustment only for gender. Here we have the model with only adjustment for age, and the crude. So now we're going to get at various forms of confounding again. In other words, we need to assess beta 1 in these 4 settings. In this setting, the most complicated one with the 5 terms, and beta 1 in the case of adjustment only for gender, here adjustment only for age, and here with no adjustment. Now the study of these 4 coefficients beta 1 enables us to determine the form of the confounding, if there is any confounding. Okay. So how is the confounding to be described here? Well, what can we see? If, in fact, we consider the model that has 5 terms in it, and it's the same as the 2 one-at-a-time models, each with 3 terms, then we could say, didn't need the elaborate model to assess confounding here. The 2 one-at-a-time models would do the trick for us. On the other hand, if in fact the value of beta 1 from the model with 5 terms is meaningfully different by some means, how you determine meaningful is an ongoing issue, but is meaningfully different from the 2 one-at-a-time models, then we could say that the age and or gender confounding is only seen through the joint analysis. And some authors then say that age and gender jointly confound. I think it's probably best to then notice that if age and gender confound and confound, and the confounding is only seen with the joint analysis, say, or the form of it, the form of the confounding we're seeing, the value of beta 1 is different with the model with 5 terms is different from the 2 one-at-a-time models, then that's the correct measure of the confounding here, the one that's seen through the joint analysis. Okay. So we could see there are a number of forms the confounding might take. It isn't just a simple of a comparison adjusted with crude. I hope that that's becoming clear here. There's a number of different issues. Now, this model that I'm showing you now, the one with 5 terms, turns out to be the same as, gives us essentially the same results as the assumed common odds ratio from a classical stratified analysis, from the stratified analysis. And we anticipate that the model-based approach or the stratified analysis approach, the Mantel-Hansel approach, will typically be very close. Okay. Now, one of the things that you need to keep in mind here is that we needed this term in order to get that closeness. And we'll be coming back to that a little bit later on in this discussion. Because we're now coming to another landmine in the use of logistic regression. So keep in mind that this is the model that should be close to the assumed common odds ratio from the classical, if I may, stratified analysis. Okay, and that's because some investigators would say, oh, we don't need to bother with that term that has the product of A and G. This so-called additive model does not. It has this lovely illusion of simplicity. There's 4 terms. We just have a term for disease status, a term for age status, a term for gender status. And that product term, beta 4, isn't there. It turns out that the estimate that we get of beta 1 here is not directly comparable with the Mantel-Hansel estimate from the stratified analysis without an additional assumption, an assumption that's often ignored in the consideration of this type of model. It turns out that the assumption has a somewhat elaborate naming, and I'll just read it for you here. The difference between the log odds of exposure for the old and for the young does not depend on gender. And that can be expressed in terms of the difference between the men and the women does not depend on age group. Now, I mean, if that assumption, it turns out to be reasonable, okay. But again, have a look at this. This is just, and you will see that in some rather elementary literature, they'll just say, we'll include these variables, the variable age and gender in the model, and that will enable us to assess confounding. Well, that turns out to be an oversimplification here without this additional assumption. Tricky stuff, eh? Absolutely. Well, at the beginning of this session, I labeled the 4 strata, 1, 2, 3, 4. And we considered, and I mentioned that we would be returning to this consideration. Let's have a look now at an analysis of the 4 strata. In other words, considering rather than the direct consideration of age and gender as potential confounders and or modifiers. How about just considering the 4 strata? Okay, so what's going on now? Well, we can then construct indicator variables for the 4 strata here. So, for example, S1 would be the indicator for the young women, S2 the indicator for the old women, and so on. Now, instead of constructing or using the indicators for men and women, young and old, and that product term that we saw, how about we just use the indicators for these 4? All right, let's do it. What happens if we were to construct a model that has all 8 terms in it, but instead of using the age group variable, the gender variable, and the product of the 2, of age and gender. Instead of doing that, if we just construct this model, well, what's happening now? Well, the first thing you might notice here is, where's S1? Where is the indicator for the young women? This brings up our next significant issue in the assessment of logistic regression models, and that is the notion of a baseline group. Here now, it turns out that the regression coefficient beta 1 is the log odds ratio for the young women. Because if we are speaking of the young women, then S2, S3, and S4 are all 0. So beta 1 here gives us the ability to discuss or describe a log odds ratio for the young women. We could do so with the other model, but it turns out that from this model involving with all 8 terms in it, we can reproduce exactly the same set of log odds ratios for the 4 different strata, as we did before. It's a relabeling, essentially, of exactly the same model that we fit at the very beginning here, the 8 terms. It turns out, although there's a little bit of math to do so, that the fitted values from this model will be identical to the fitted values from the other way we represented the model with 8 terms in it. Where we had, remember before, we had beta 7 AGD over here, right? So what are we getting? The fit's the same, but now we can see, the regression coefficients are not the same. But again, with a little bit more sort of math type stuff, we can see that the regression coefficients we get here are merely linear combinations of the regression coefficients we got back with with the original model that had the 8 terms where we used age and gender instead of the 4 strata. So you can see here that there's a certain amount of newness to this, apparent newness. Now, again, what I would encourage you to do is to interpret all of the regression coefficients again in this representation of the model, and you will see very different things. What you will see is comparisons then with the young women. When the baseline group here is S1 and it's excluded from this model, then the comparisons that are crucial become comparisons between a particular group, a particular strata, and the young women. So there's a fair bit going on here, and we will see this particular representation popping up from time to time. So this is just repeating what I just said. It turns out that the model that we had in the previous slide and this model give us exactly the same fitted values. Further, it turns out that the omnibus test of beta 5 equals beta 6 equals beta 7 equals 0 is the same as the test that we would have gotten if we had done so with the stratification variables, S2, S3, S4. In other words, the 2 tests are identical. The test for homogeneity of the odds ratios will be the same as in the classic stratified analyses. But now the individual coefficients in the 2 models address different issues. Rather than directly addressing, for example, whether or not age modification depends on gender, or gender modification depends on age, this model involves comparisons directly with the young females, rather than the issues of age and gender. And you could say that perhaps that's a weakness here. Why would you want to use this? Well, probably you wouldn't in this instance. But on the other hand, you might have a circumstance in which there are 4 qualitatively different strata, and this would be the model to select. And then we would have the ability to make comparisons with a baseline group. This turns out to be valuable in certain practical contexts. that really the issue is about comparison with a particular baseline strata. Okay. Another point that can be made, it turns out that these two models have the same fitted values and the same estimate of beta 1. Notice that these two models are the model that is the most complicated one for assessing confounding. Now, what it says is that if I have S2, S3, S4 terms here, that enables the assessment of adjustment for strata, just like this model does. Now, this brings up another point, in that you can see, I think, fairly directly that I need these three terms for the adjustment for strata. And it isn't entirely obvious that we need these four terms, or these three terms here, for adjustment when we have age and gender. But in fact, these two models yield the same estimates of beta 1 and yield the same fitted values. So I'll reinforce then that this is the model that is the basis for assessment of confounding when you're considering this process. Keep in mind that if I am prepared to assume that beta 4 is 0, then I am not doing the same thing as the classic stratified analysis, and I'm not doing the same thing as might be warranted here in this instance. One more point that I'll make here on this set of slides, and that is that if we have the model with all 8 terms, it is possible to interpret any of the individual regression coefficients. What did we do? We focused our attention on beta 7, then we removed it and considered the interpretation of beta 5 and beta 6. Maybe the most common scenario. On the other hand, it turns out that there are practical circumstances in which one might, before consideration of all of these terms, beta 7, beta 6, beta 5, address another term like beta 4 here. It might be that there's some sound consideration, perhaps from your literature, that this is the issue that needs to be addressed first. Notice this is a somewhat elaborate circumstance, but if beta 4 is 0, then it's saying that among the controls, the difference between the log odds of exposure for the old and the young does not depend on gender. You might be thinking, when would that ever come up? Well, it turns out there is an illustration of this that we will be seeing, or that in fact can be described. A real, if I may, real circumstance. Further, in this particular actual so-called real, I guess I'll say real, in that it is indeed a study that was undertaken, the investigators wish to address beta 4 being 0 first, before assessing beta 7 and so on. It turned out that by careful consideration of beta 4 first, and then removing it, and refitting the model without beta 4 here, we gained more sensitivity in the assessment of beta 7 and so on. A very interesting scenario. So there's a lot of different models that can be considered. As I mentioned, in principle, there's a huge number. There's 256 of them in this instance. And it's true that most of the time we'll follow an epidemiologic paradigm that suggests moving from the most complex to steadily less and less complex. Sometimes the terminology of backward elimination is used here. That phrase I've never been terribly thrilled with, but it's out there. backward elimination, starting complicated and then reducing. All right, let's now return to that session 2 example that we worked through in detail using Stata, where I showed you the Stata window in all of its pieces. What did we have? Well, we went through a fair bit of it. Here is just a quick review, and then we'll look at the logistic regression equivalent. So we had, in fact, in this illustration, the stratified analysis. We got these 4 quite different estimates of the odds ratio. Very different, and I won't repeat this. But as we noted, for example, this first number here is the odds ratio estimate for the young women. And in fact, you can compute it directly just to check that using AD over BC. Okay. And we can consider the fact that that chi-squared test with 3 degrees of freedom is way out in the tail. Okay. Another way to check that it's not 0, but it's an extremely tiny number. And we've gone through some of this. I won't repeat it all. The omnibus test for modification has a low p-value and indicates strata modification. But the test does not per se tell us how age and or gender modify. And we can see further that since modification has been detected quite without any qualification, there's modification here, that we have no business addressing confounding here. And we won't bother with that. So that Mantel-Hansel test that's reported here, we can cross out with a red pen. And what did we do? We did the 2 one-at-a-time analyses, which we discredited. We saw that both of them involve oversimplifications. Okay. We see that simultaneous stratification on age and gender is needed here. We need both. How about the models that would be needed to address this? Well, we need to start with the model that has 8 terms. So we need the product of age and gender, the product of age and exposure, the product of gender and exposure, and the product of age and exposure. There's the 4 terms that we need that were not directly computed. We do that using the generate command, or GEN, in Stata. Then we get, whoa, the big model with all 8 terms. Keep in mind that the constant term is not listed here by convention, but it's not included in the list. It looks like there's only 7, but in fact the constant term is always included. And then what do we see? Okay. Oh yes, I was going to note that we can directly compute the estimate of the log odds of disease for the unexposed young females. And I could have computed that directly. Okay. From the data. Okay. There's other pieces we can directly interpret here. For example, this number associated with the variable age, minus 0.203. We can see that it is an estimate of the log of the ratio of odds of disease for the old relative to the odds of disease for the young, but specific to the unexposed females. Right. They all have interpretations. Many of them can be computed directly by directly from the tables. You can see that here. Okay. But now we can come to maybe the biggest, I guess, prize of our logistic regression here. And that is the estimate of beta 7. So we've interpreted some of the other pieces here, but the real issue is, how about we look at the estimate of beta 7. The estimate of beta 7, B7, minus 5.82, it's big. And what is it? It's an estimate of the log of the ratio of two odds ratios. And it's telling us about whether age modification is modified by gender, which we saw was the same thing as asking, does gender modification depend on age? Aha! So what do we get? We get something we did not get from the stratified analysis. We get an identification that I think was hinted at from the values of the four stratum-specific odds ratio estimates that we got from the stratified analysis. But that we're getting that the age modification depends on gender and vice versa. And we have a test of significance for it. And it's very small. The Z, the Wald test here, minus 7.51. Wow. Further, we can construct the two specific log odds, or the logarithm of the ratio of odds ratios, males relative to females specific to the young. And so this is telling us about gender modification, but specific to the young. And we could also interpret beta 5 here, which is telling us about age modification, but specific to the women. Okay. In this particular instance, with beta 7 clearly non-zero, we don't have a consideration of any other models. However, for interest, you may wish to consider what might be the failures here and interpret these pieces. And you'll recall that we had an assumed common part to the number minus 0.87 and the minus 0.261. They both involve the logarithm of the ratio of two odds ratios assumed common. But we've discredited the assumed common part. We've already determined that the logarithm of the ratio of odds ratios depends on the other. In other words, if we consider the logarithm of the ratio of odds ratios young to old, it depends on gender. And similarly with age modification. Okay? And similarly with gender modification. So the model that dropped beta 7 is misleading us. It would be incorrect to use this model. The same challenges apply to the two one-at-a-time models. And in fact, you may wish to compare the results you get here with the one-at-a-time classical analyses that we did initially in session 2 and are reproduced up above in the slides. Sure enough, we get the right coefficients insofar as they correspond to the corresponding stratified analyses, but neither of them are right. They're both incorrect. They're both discredited. So none of these later analyses are of any merit. It is we can discuss them academically and wonder about what the implications might have been. But the fact that beta 7 here, this number here, is clearly non-zero is the big picture issue here. And we could then, again, as we did, discuss the interpretation of these two numbers and in fact, note that the issue is complicated, that the 4 stratum-specific odds ratios are different in ways that need to be further explored. Okay, continuing with session 4, I have a second example for you that I would like to spend a few minutes with and get to the key issues here. As we did before in session 2, you could use Stata to display the 4 different 2x2 tables and individually compute the odds ratios and the various pieces from that stratified analysis. Let me cut to the chase here. What have we got? Let's see. The test of homogeneity is not significant. What's going on here? Right, this is omnibus. It's based on 3 degrees of freedom. Right. What can we see? If we key on the young, we see we get odds ratios of about 2. If we key on the old, we get odds ratios that are more, about more than 3.3. So we might ask, is there modification by age? That's interesting, isn't it? In other words, well, this odds ratio, all 4 of these odds ratios are greater than 1, so we may be looking at a comparatively subtle issue here. But on the other hand, if in fact the odds ratio or the strength of the association between disease and exposure is more for the older people than it is for the younger, then that might be something that could be worthy of reporting. Okay. On the other hand, you might say the homogeneity test is not statistically significant here. And so you might say, let's compare the adjusted with the crude, and if we do so, we see what appears to be confounding. It's a big difference here, isn't it? Difference between 2.5 and 0.46. Well, they're pretty different. Okay. The crude and adjusted are very different. On the other hand, what happens if I was to consider an analysis, a one-at-a-time analysis now, where I stratify only on gender? And you can see again, I don't see much. Right? Adjusted only slightly different from the adjusted we got here. No evidence of homogeneity. And a Mandel-Hansel test that's again saying, yes, there's a disease exposure relationship. Fair enough. Got that in play, right? On the other hand, let's go back again and look at this set of 4 2x2 tables, or 4 odds ratios. Pretty clear that adjustment for gender only looks somewhat speculative because of the fact that the age differences are seen here. Maybe minor, maybe modest, right? On the other hand, if we were to stratify only on age, All right? We don't see any difference between the two age-specific odds ratios. But notice again here that the numbers involved here in this one-at-a-time analysis, the 0.41 and the 0.50, aren't anywhere near this number that's about 2 and this number that's about 3. Uh-oh. It does appear as though we're being led astray by these two one-at-a-time analyses. I hope that's fairly clear. All right. It appears that the one-at-a-time analyses are missing something. It appears that there's a confounding issue and maybe a modification issue. So let's then consider the stratification by age, but adjusted for gender. Excuse me. the consideration of the age specific now analyses, where we'll just consider the young and ask, what about these two numbers? The comparison of these two numbers. That is, the two age-specific odds ratios, but just for the young. And what do we see? Nothing. No issue here. Let's do it for the old. What do we see? Notice that now we're comparing quite different Mantel-Hansel numbers. This number of 2.04 that we got from a stratified analysis but specific to the young gives us a number of 2, whereas this number of 3.3 is the Mantel-Hansel but specific to the old. Okay? Still, though, no evidence that there's any modification by gender here, right? Neither here nor here. These two numbers are close. These two numbers are close. However, they're not the same. This adjusted is not the same as this adjusted. And that maybe is about as far as we can take this assessment with the classical stratified analyses. So let's try the logistic regression approach. And now this is going to take us back to where we, I think you're going to really like this. I hope you do. Because now we can take the model that has all 8 terms in it and first begin by the testing of whether or not age modification depends on gender. And we see that there's no evidence of that. And you may find it of interest to consider this. So age modification doesn't appear to be modified by gender. That p-value is huge, and the value of that regression coefficient here is small. Okay. You may find it helpful to review how, in fact, that number is obtained. So what did we get? We got the various pieces in this analysis. You can take some time with the rest of this text that's written here. Now let's proceed with an assessment of the model that allows for an assumed common odds ratio and an assumed common ratio of odds ratios, So it's young versus old, or young over old adjusted for gender. Remember, now this is getting closer to what we were seeing in the display. So that number there, 0.4865, is an estimate of the log of the ratio of the assumed common odds ratios. Okay, so we've got two odds ratios, assumed common for gender, and that's the estimate of that assumed common ratio of odds ratios, adjusted for gender. Assumed common for gender. The number minus 0.05 is the same thing, but now it is assumed common for age. Now that one, we could say, well, we haven't got much going on there. Now, here is an instance in which, again, we're trying to follow the modeling process in a sensible way. There are a huge number of models that could be considered here, and we're attempting to consider a modeling process that has some currency, has some sensibility, appears to be leading us in the right direction. So what I'm going to then show you is the model that removes this term GE and refit without GE. Let's just observe what happens when we do so. When we remove GE, well, how about that? We get a measure of this logarithm of the ratio of assumed common odds ratios adjusted for gender, right? This is age modification adjusted for gender, and it's about the same as we got in the previous case, but now you're getting into that borderline range. Is this actually a meaningful, detectable thing? And again, I'm grasping a bit here, but this is, again, a fairly elaborate illustration, but I hope I'm leading you to what I think is a sensible set of affairs. What happens if we delete GA? Okay. What are we doing now? All right. We have a model that provides for age modification adjusted for gender. Again, this coefficient, not that materially different from the ones we've seen in the previous two. But this is the closest we're going to get to a situation in which gender needs to be in the model that includes exposure, age, and the product of age and exposure. In other words, this is the model that provides for age modification adjusted for gender. There's a lot that you might say, wow, you're really on a fishing expedition here, Gordon. Any justification for this? Well, it's getting a little borderline, I would argue. On the other hand, this is an instance in which many investigators would say, we have now evidence that age modification is present, but it's only seen if I adjust for gender. So we can consider this model again, now with the regression coefficients exponentiated, and perhaps get a tiny bit more to this piece. This particular model is the model that we would have, if we had decided from the outset to consider age modification with adjustment for gender, then this is the ratio of odds ratios estimate, right? After adjustment for gender, because gender's here in the model. Big numbers. All of this would need to be checked. Here we've got an odds ratio of 17. Whoa, what does that mean? So there's a fair bit that is maybe a bit tenuous. However, let me just repeat this. we followed the path of deleting terms and gotten to the model that provides for age modification adjusted for gender. Okay. In fact, we can see that if we take the exponent of the coefficient and then multiply the terms, this term 2.03 and the 1.64, then we're getting the two numbers that we might have seen as the most relevant. In other words, these two numbers, the exponent of this coefficient estimates gives us numbers very close to what we saw from the classic analysis. So we appear to be in a place, because of the p-value being less than 1%, that we have evidence of age modification. Now you saw what the actual real differences were here. But this could be an important finding. And we saw it after adjustment for gender. Right? It is worth noting that if we had not adjusted for gender, we would not have seen it. Again, we saw this back in the one-at-a-time classic analysis that was done earlier. So, if you're on side with what I've shown you here, we have then evidence of age modification. But the age modification is confounded by gender. And this confounding is identified by comparing the two estimates, and is identified by noting there is statistical significance with the adjusted, but there is no statistical significance with the crude. And that is one way of arguing for confounding here. Fair bit in play, you might say. So just to repeat, this number, where we've looked at age modification after adjustment for gender, is not the same as this term where we did not adjust for gender. And so we could say that this is a circumstance in which we have a form of confounding. But it's not simple crude with adjusted. Or is it? This number, or this model, gives us this measure of age modification, which we could call crude in the sense that it is not adjusted for gender, whereas this one is adjusted for gender. And with that, we will close Session 4 on models in epidemiology and biostatistics.